Welcome back to ECE 320A. In this video, what I want to do is show one technique for finding the actual or exact expression for a transform that does have repeated real poles. And in another video, we will look at finding alternative ways to finding these partial fraction expansion coefficients. Here's our example that we want to work on. Suppose that we now have a transform that has a numerator 2s plus 1 and a denominator that is cubic, and it now has a repeated root at s equal to minus 1. It's repeated twice, and we have a distinct pole at s equal to minus 2. We can then start putting through the terms. We have a cubic, so we should have 3 partial fraction expansion pieces. We have 3 terms here. We have an A1 sitting on top of the full repeated roots at s equal to minus 1. We have s plus 1, that quantity squared, and then we just keep decreasing the power on that s plus 1 factor until we get down to a power of 1. So in this example, that just means that we have one additional term, an a sub 2 over s plus 1 raised to the first power, and the partial fraction expansion piece associated with the distinct pole at s plus, or associated with the factor s plus 2 gives rise to the a sub 3 over s plus 2. From this, I want you to be able to immediately write down the structure for f of t. And the structure, by that I'm meaning I just want to see the exponents and the frequencies. I'm not so much worried about the weightings or the coefficients. But in this particular case, back from what we've talked about before, we now know that we have an a sub 1. Now we have a square there, so we have a t, e to the minus 1t. I'll go ahead and emphasize the 1, plus an a sub 2, e to the minus t. Again, there's a 1 there also. Sometimes it's going to be there explicitly, or maybe it won't. It'll just be e to the minus t, plus a sub 3, e to the minus, and we have to show that because that is something other than 1, and that's true for t greater than or equal to 0. And in this particular case, then, I hope you can see that the 1 here is giving rise to that 1. This 1 is there, and that 2 gives rise to the minus 2 in the exponent. What's different here is that that 2 now gives rise to a t sitting in front of that first partial fraction expansion piece or term. Now what we want to do is actually find an exact expression for f of t. We want to actually evaluate or determine these residues a sub 1, a sub 2, a sub 3, so that we can get the exact. If I just ask for a structure on an exam, then that's what it would be. You could also write this structure as a1t e to the minus t plus a sub 2 e to the minus t plus a sub 3 e to the minus 2t, all switched on, or only true when t is non-negative, and that happens by scaling or switching those terms on with the unit step u of t, which is only 1 when the argument is non-negative, or when t is greater than or equal to 0. So you might see me writing f of t as either the top expression or the bottom expression, and that just contains the structure for f of t. What we now want to do is look at the exact expression. So we're trying to now find these values for a sub 1, a sub 2, and a sub 3. With that being said, now you have to ask your question, can we find any of these a1, a2, and or a sub 3 using the traditional cover-up method that we've been using most of the time, or all of the time, when we had distinct roots? here what you can do is you can actually use the cover-up method. I think it's pretty clear that you can use that for a sub 3. That's a distinct pole. But now, here's where you might get tripped up. We can also use the cover-up method for the coefficient associated with the highest power of the repeated root. And in this case, we have an s plus 1 quantity squared, and we've identified the coefficient for that to be a sub 1, meaning we can now use the cover-up method to find both a sub 1 and a sub 3. So let's now find those two expressions or values, numerical values, using our cover-up method. We then multiply to find a sub 3. We multiply the left side by the factor s plus 2, and the right-hand side we multiply by s plus 2. And by evaluating that at s equal to minus 2, everything vanishes on the right except for a sub 3. So we have a sub 3 is equal to, and now we have a 2s plus 1 over s plus 1 squared, and we're evaluating that at s equal to minus 2. Or we now have 2 times minus 2 plus 1 over minus 2 plus 1 quantity squared, which we have minus 4 plus 1 upstairs, or we now have minus 3, over 1 minus 1 squared down below, which is 1, or we now see that a sub 3 is actually minus 3. A sub 1 we can find in the same way. We multiply all terms by the factor s plus 1 squared, which cancels a lot of things out and leaves us with a sub 1 equaling 2s plus 1. The only thing left in the denominator when we multiply f of s by s plus 1 squared is the s plus 2. And we evaluate that now at the value that causes the factor underneath a sub 1 to vanish, which is s equal to minus 1. Or now we have 2 times minus 1 plus 1 over minus 1 plus 2. We now have minus 2 plus 1, and that's all over 1, or this now becomes minus 1 for our value for a sub 1. We've now found a sub 1 and a sub 3. We can't use the cover-up method for a sub 2. We'll just get infinite equal infinite, and a sub 2 will be swamped by that right-hand side and left-hand side, so we can't find a sub 2 using the cover-up method, but there are many ways to find that a sub 2. Let's just, for quickness sake, or for this particular example, let's use one, and one such technique is to just select. Remember, our partial fraction expansion formula is true for all values of s. Let's now use a convenient value of s to find that one remaining residue or partial fraction expansion coefficient, a sub 2. So now we want to select a convenient value for s. And what we can't do is when we're looking at this expression, a convenient value of s is not a value of s that causes any of those denominator terms to vanish. So we couldn't use s equal to minus 1 because then we would get nonsense. We can't use s equal to minus 2, but we can use any other value of s that's convenient in quotes, and that just means pick a value of s that will allow you to do the algebra maybe a little bit more easily. That's convenient value of s. In this case, we could put in maybe an s equal to 0, and that causes a lot of these pieces to vanish, but we still need to keep track of a sub 1 and a sub 3 and what we've numerically calculated those to be. In this case, let's go ahead and select a convenient value of s to be 0. And doing that, now we have 2 times s, which now we're letting equal 0, plus 1, over s plus 1 squared. Everywhere we have an s, we're replacing it with 0. S plus 2. So all of those s's now have been set equal to 0. We had a sub 1, which we've now determined previously. That was minus 1 over s plus 1 squared. Again, the s gets replaced with 0. A sub 2, we still don't know, and luckily that's what we're trying to find, so that's still an unknown coefficient. S plus 1 is underneath it, plus a sub 3, which we do have, and that's sitting on top of 0 plus 2. Now we have one equation in this one unknown, a sub 2, and hopefully now we can do the algebra. We should see that on the left-hand side, upstairs, we're just left with 1. Downstairs, we have 1 squared times 2, or 2. So on the left, we have 1/2. On the right, we have minus 1 divided by 1, or minus 1. A sub 2, conveniently enough, is divided by 1, so that's now a sub 2. And the last term is then minus 3/2. If we now simply do the algebra, if we add 3/2 to both sides, we end up with 4/2 on the left equaling minus 1 plus a sub 2. And that gives us 2 equal to minus 1 plus a sub 2. We add 1 more to both sides, and we now have 3 on the opposite side from a sub 2. So a sub 2 is actually 3. Now we have an exact expression for f of t. A sub 1 was minus 1, and that was associated with the stick a t in front of it term, t e to the minus t. A sub 2 was the unt'd exponential of the minus t structure. So we now have plus 3 e to the minus t, and then we had a minus 3 for a sub 3, which was the coefficient associated with the mode e to the minus 2t, and that was going to be for this one-sided transform, or this is true, this expression, when t is greater than or equal to 0, or for non-negative values of t. That's now our exact formula. It has more than just structure. Now we've identified those residues, or those partial fraction expansion coefficients, and we've had to use a new technique beyond the cover-up in order to find that one remaining coefficient, in this case a sub 2.